Electric vehicles, EVs, are reshaping transport, and EV chargers are the critical link between the grid and your car's battery. In this video, we'll explain clearly how EV chargers work, the different types, how efficient they are in real life, what affects charging speed and battery health, costs and installation, safety and standards. What is an EV charger? An EV charger is a device or system that transfers electrical energy from a source, usually the electricity grid, into an electric vehicle's battery. Chargers either supply alternating current, AC, that the vehicle converts to direct current, DC, via an onboard charger, or they supply DC directly to the battery using an offboard converter. Beyond simple power conversion, chargers manage safety, communicate with the vehicle, negotiate charging limits, and often handle authentication and billing. Two main places conversion happens: onboard versus offboard. Onboard charger, OBC, located inside the vehicle. It converts AC from a home or public level 2 charger into DC suitable for the battery. The vehicle manufacturer sizes the OBC. Common capacities range from 3.7 kilowatts to 11 kilowatts or more in three-phase vehicles. The OBC limits how fast an EV can charge on AC power. Offboard DC fast charger, DCFC. The AC to DC conversion happens in the charger equipment outside the vehicle, enabling much higher power delivery directly to the battery, 25 kilowatts to 350 plus kW. DCFCs bypass the OBC and are essential for rapid charging on highways and commercial depots. Charger types and real-world use cases. Level 1. Slow AC uses a standard household outlet, typically 120 V in North America. Power is 2.4 kW and adds only a few miles per hour of charging. Best for overnight charging if daily range needs are small. Level 2. Fast AC uses dedicated circuits, 208 to 240 V single-phase or three-phase in many regions. Power typically ranges from 3.7 kilowatts to 22 kilowatts. Common home/workplace units are 7 to 11 kilowatts. Adds 20, 80 plus km, 12 to 50 miles per hour depending on vehicle and power level. Ideal for home overnight charging and workplace charging. DC fast charging / level 3. Powers from 25 kW up through 50, 150, 250 to 350 kilowatts and beyond. Provides fast top-ups for long trips, e.g., 10% to 80% in 15 to 40 minutes for many modern EVs at high-power stations. Used for highway stops, fleet depots, and commercial applications. Connectors and communication protocols. Several connector standards exist globally. CCS, Combined Charging System, is widely used in Europe and North America and supports high-power DC charging. CHIMO originated in Japan and is still in use for some vehicles. Tesla uses its own NACS connector, now being adopted more broadly. China uses GB/T standards. Besides physical connectors, chargers and vehicles communicate via protocols. Basic AC charging uses pilot signals, IEC/SAE standards, while DC charging and advanced features use higher-level protocols like ISO 15118. ISO 15118 enables plug-in charge, automatic authentication, and billing, and can support future vehicle-to-grid V2G features. Step-by-step, how a charging session works. 1. Plug and handshake. You plug the cable in, or a robotic connector connects. The vehicle and charger verify mechanical interlocks and safety readiness. 2. Authentication. The station may require authentication via RFID, app, credit card, or plug and charge certificate exchange. 3. Negotiation. Vehicle and charger negotiate maximum allowable voltage and current, taking into account battery state of charge, SOC, temperature, and BMS limits. 4. Power transfer. AC is converted onboard, level 2, or DC is supplied directly, DCFC. Charging current may be adjusted dynamically. 5. Monitoring. The BMS and charger monitor voltage, current, temperature, and safety. Charging current typically tapers as SOC approaches full to protect the battery. 6. Stop. Charging ends automatically at the target SOC or when the user ends the session. Session data may be logged for billing. Efficiency. How much energy actually reaches the battery. Charging efficiency is the fraction of energy drawn from the grid that is stored in the battery. Losses occur in power electronics, cables, connectors, and inside the battery due to internal resistance and heat. Typical figures: AC charging via onboard charger. Conversion efficiency of the OBC is roughly 85 to 95%. Considering other minor losses, grid-to-battery efficiency often falls in the 80–92% range. DC fast charging. Modern DCFCs use high-efficiency rectifiers and power electronics. AC to DC station efficiencies are commonly 92 to 96%. Considering cable and battery acceptance losses, grid-to-battery efficiency is often 88–95%. Battery charging acceptance efficiency varies with SOC, temperature, chemistry, and charge rate. Batteries accept charge most efficiently near moderate SOC and moderate charge rates. Very high power charging or extreme temperatures increases heat losses and reduces effective efficiency. So slower charging is sometimes slightly more efficient, but the gap is not enormous with modern equipment. The most efficient real-world option for daily use is usually home charging with off-peak electricity, both economical and gentle on the battery. What determines charging speed? Charger power. Higher kW rating means more potential charging power. Vehicle acceptance. The battery's maximum charge rate, kW, limited by the BMS and thermal system. State of charge. Charging power is highest at low SOC and tapers above 70–80% to protect cells and reduce heat. Battery temperature. Batteries charge fastest when within an optimal temperature window. Cold batteries accept charge slowly until preconditioned. Grid and station constraints. Available feeder capacity, number of simultaneous users, or site power limits can reduce delivered power. Cable and connector design. High-power charging sometimes requires liquid-cooled cables to carry heavy currents safely. Effect on battery health. Frequent high-power charging can accelerate battery aging if not managed properly, because it increases battery temperature and stress. Modern EVs mitigate this with active thermal management, adaptive charging curves, and charging protocols. Occasional DC fast charging has minimal impact for most users. Best practice: use fast charging when necessary, long trips, quick turnarounds. But do daily charging at moderate speeds, level 2, and avoid keeping the battery at high SOC for long periods. Costs: equipment, installation, and operation. Home level 2. Chargers often cost $300 to $1,200 for the unit. Installation $300 to $2,000 depending on electrical work. Operating cost equals electricity price. Off-peak rates lower cost per kilowatt hour. Public level 2. Installed cost $2,000 to $10,000 plus, including networking. Operators set pricing per kilowatt hour or per hour. DC fast chargers. Equipment and site costs can range from tens to hundreds of thousands of dollars depending on power. 50 kilowatts versus 350 kilowatts. Grid upgrade needs, civil works, and energy storage integration. High commercial costs are offset by usage fees, but require good site selection and utilization to be profitable. Energy cost considerations. Public DCFC rates often reflect not just energy, but demand charges, maintenance, and convenience. Many hubs price per minute or per kilowatt hour. Safety and standards. EV chargers include multiple safety features: ground fault detection, isolation monitoring, emergency stop, interlocks, temperature monitoring, and overcurrent protection. Standards and certifications ensure safe design and installation. IEC 61851, SAEJ 1772, ISO 15118, UL listings, and national electrical codes. Proper site installation and maintenance are essential to ensure reliable and safe operation in public and private settings. Real-world limitations and challenges. Grid impacts. High-density charging, especially DCFC clusters, can stress local transformers and distribution networks. Managed charging, local storage, and grid upgrades are common solutions. Availability and reliability. User experience depends heavily on charger uptime, network reliability, and station maintenance. Poor reliability undermines confidence in EVs for long trips. Interoperability and payment friction. Varying authentication systems, roaming agreements, and pricing cause frustration. ISO 15118, plug-in charge, and better roaming improve the user experience. Equity and access. Not everyone has home parking for a charger. Public and curbside charging solutions are essential to serve apartment residents and renters. Cost of fast infrastructure. DCFC is expensive to deploy widely. Targeted deployment at highways, retail hubs, and fleet depots improves ROI. Advanced features and the future smart charging. Shifts charging to off-peak times or when renewables are abundant and responds to grid signals to reduce costs and grid stress. Vehicle-to-grid. V2G allows bidirectional energy flow so parked EVs can provide grid services or emergency backup. V2G adoption depends on standardization, battery cycle impacts, and compensation models. Ultra-high power charging. 350 kilowatts and above enable faster highways charging, but require grid upgrades and liquid-cooled cables. Battery and vehicle innovations. Higher acceptance batteries, improved thermal systems, and solid-state cells could shorten charging times and improve longevity. Integration with storage and renewables. Co-locating batteries and solar with charger sites smooths demand, reduces demand charges, and lowers the carbon footprint. User experience improvements. Universal connectors, easier payment, plug-in charge, better reliability, and station reservation systems will simplify charging. Practical advice for EV owners: most daily needs are met by home level 2 charging. Install a dedicated circuit and a smart charger if possible to schedule off-peak charging. Use DC fast charging for travel and occasional quick top-ups, not as a daily habit unless your vehicle and job require it. Precondition the battery, heat it when cold, before fast charging to speed acceptance and reduce stress. Monitor battery SOC habits. Avoid maintaining 100% SOC for long periods and avoid frequent deep discharges to maximize battery life. Choose charging networks and apps that offer good reliability, clear pricing, and easy payments. Consider membership plans if you frequently use a particular network. Conclusion: EV chargers are mature technology that enable the electric mobility revolution. Their real-world effectiveness depends on matching charger types to needs. Home and workplace level 2 chargers are cost-effective and efficient for daily driving, while DC fast chargers enable long-distance travel and rapid turnaround at higher cost and infrastructure complexity. Charging efficiency from grid to battery commonly ranges from about 80% to 95% depending on hardware, charging rate, and conditions. As batteries and chargers improve, and as grid integration, storage, and smart charging proliferate, charging will become faster, cheaper, and greener, making EVs even more practical for more people. If you like this explainer, consider using it as a YouTube script. Start with the high-level overview. Show visuals of level 1 to 3 chargers and connectors. Include an animation of AC versus DC conversion. And close with practical owner tips and future trends. If you enjoyed this video, don't forget to like, subscribe, follow, and hit the notification bell for more tech deep dives like this. Until next time, stay curious and keep exploring this tech in minute.